Hi everyone. With this lecture is the first of four related to the broad topic of the chemistry of life. So this one I'm going to do a little bit of basic chemistry about the structure of the atom, then we'll get into bonding, and then we'll get into biological molecules like water, carbohydrates, proteins, and fats. I can't make the PowerPoints real long because the size of them they become too hard to save and to download. So that's why I have them broken up into four smaller ones. So if you've already had chemistry, and I probably some of you have, this lecture will be kind of a review. If you haven't had chemistry, it's to give you a little bit of the basic chemistry to help you understand some of the other biological things we'll be talking about throughout the semester. So chemistry is the study of matter. And technically, matter is defined as anything that has mass and takes up space. So it's kind of everything. Even things that air, for example, doesn't seem like it takes up space, but it does. You can fill up a balloon with air and it looks inflated. If you had a really good balance to weigh that, you could see that an empty balloon weighs less than a full balloon. So it follows the category that it has mass and it takes up space. All matter can exist in three different states: solid, liquid, and gas. And usually we refer mostly to the state they are at normal body temperatures or living temperatures. So for example, water is a liquid. If you heat it up and boil it, it's going to turn into a gas. And if you put it in the freezer, it's going to turn into a solid. But all substances can go into those three states. We tend to be more familiar with one that exists, like oxygen is a gas at usual temperatures that we're around. So we think of it as a gas, but if it got really cold, it could turn into a liquid, and even colder, it would be a solid. There are about 92 different elements that make up all matter on Earth. And those are the naturally occurring elements. There are some man-made elements that actually make the total number of elements a little bit bigger. And I'm going to show you the periodic table. And so even though there are that many different elements, most of the mass of living organisms is composed of just 6 of those 92, and that's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, which if you want to remember them, that's called schnapps. And so all living things, not just humans, but anything composed of cells, those are the 6 primary elements. And the reason they're the major ones is because they're the big macromolecules, and water are composed of those elements, so that's why they are the major component of living things. So this shows you all the elements. They are arranged by something called atomic number, which I'll talk to you in a minute. The ones that have the kind of shadowy letters are the man-made ones that don't exist naturally. And this little section here actually gets stuck in right there, but they have it separate so that the table doesn't look so odd. And the ones that we'll be talking most about are those 6, and they're kind of all up at the top of the table, of the periodic table. Like here's carbon, nitrogen, oxygen, hydrogen. That's 4 of them. Phosphorus and sulfur are the other 2. So those are the 6 most common. So the rest of these are present. Things like calcium and sodium are present in living cells, but they're not major components of living cells. And again, this is showing you the elements, in this case, of the human body. And here is oxygen, carbon, hydrogen, nitrogen. They're by far the most common. They make up about 96%. And then things like sulfur, phosphorus, calcium, sodium are the rest of the major components. Then there are some that are present in really small amounts. And we'll be talking about some of them as we go through the semester. For example, iron. So iron is a component of hemoglobin, which is the protein in your red blood cells that transports oxygen. So even though it's present in our body in very small amounts, it still has a very important function. Iodine is a component of thyroid hormone. So again, it's a very small component of our overall body weight, but it still has important functions. So these are called trace elements, the ones that are present in really small amounts, but some of them have important functions that are essential to our cells performing normally. So all matter is composed of atoms. So just like we talked about that the cell is the smallest component of living organisms, the atom is the smallest component of matter. There are things smaller than an atom, but in order for it to be a unit of something like sodium or carbon or hydrogen, it has to be at least an atom. So the atom is the smallest unit of an element. So if you have something like a piece of gold, it's composed of millions or billions of atoms of gold. All atoms have subatomic particles, which are inside of one atom. So there's like the smaller components that make up the structure of an atom. And there are three of them that we're going to talk about: protons, neutrons, and electrons. So protons have a positive charge. They have a weight, it's called 1 Dalton. That's after a scientist named Dalton. But because all of your mass or weight, there's a slight difference between mass and weight. Mass is actually the weight, the mass of the atoms. Weight is influenced by gravity. I tend to use them interchangeably because gravity is the same wherever we are on Earth, so we kind of don't have to think about them. So the protons are found in the nucleus of the atom. So the nucleus is like the inner core of an atom. I'll show you some pictures in a minute. Neutrons, as you can kind of guess from the name, are neutral. That is, they don't have a charge. They weigh about the same as a proton, and they're also in the nucleus. The third type are electrons. Electrons have a negative charge, opposite and equal to the positive charge. They have a very, very small weight. So a proton is 1 Dalton, a neutron is 1 Dalton, an electron is 1/1836 Dalton. So we kind of ignore the mass of electrons when we're considering the mass of an atom. But since they are matter, they have to have mass. And so they do have a mass. It's just so small compared to the protons and neutrons that you can kind of ignore it. They are not found in the nucleus, but spin in shells around the nucleus. So let me show you a picture. So all atoms contain certain numbers of protons, neutrons, and electrons. And what determines what element an atom is the number of protons. So the number of protons is very important. So for example, carbon, has 6 protons. And so anything that has 6 protons is carbon. If you were to somehow stick another proton in there, it would then have 7, and it's no longer carbon, it's nitrogen. So the number of protons determine what element that atom is. So this is just some pictures. So the nucleus is the innermost part, and it contains all the protons and the neutrons. And then the electrons spin around the nucleus. This is the kind of picture you tend to see showing the spinning of the electrons around the nucleus. It's somewhat misleading because it looks like the electrons have specific orbitals, kind of like the path of the Earth around the sun and the moon around the Earth. So you can kind of always say where they are, but electrons actually spin much more randomly than that, so they don't really have a specific orbital. So sometimes you'll see pictures like this, where it's kind of this electron cloud there to show that this is where the electrons could be, but at any one instant in time, you can't exactly tell where they are. It's kind of like if you have a ceiling fan and you have it going on really fast, the blades just become kind of a whir. You can't see individual blades. And so you can't really say at any point in time where a blade is, but yet you know they're there. Electrons actually are much faster than ceiling fan blades, so it's even harder to tell where they are. So again, this is just a recap. So protons have a positive charge, a mass of 1, they're in the nucleus. A neutron has 0 charge, a mass of 1, and it's in the nucleus. So these are the two that make up the nucleus. An electron has a negative charge, it says 0 mass, but it's just really tiny, and it's in the shell surrounding the nucleus. And the size of a nucleus is very, very small. You cannot see this with your naked eye. Even with any microscopes you would have, you wouldn't be able to see the size of the nucleus or the size of an atom. And within the atom, the nucleus is very tiny, so that those protons and neutrons are kind of like very tightly compacted in the center of the atom, with the electrons spinning around. In the periodic table, which I showed you earlier, every element, every one of the 92 elements is given a symbol. It's either 1 letter or 2 letters. If it's just 1 letter, it's always a capital letter. If it's 2 letters, the first one's capital and the second one isn't. And some of them have letters, many of them have letters that refer to their name, like C is carbon. The problem is there's lots of elements that start with C. There's carbon, cesium, chlorine, calcium, copper. So C was taken by carbon, so all those other ones have to have, like, copper is Cu and calcium is Ca. So those kind of make sense. Some of the elements have symbols that don't make a lot of sense because they're based on Greek or Latin. For example, Na is sodium. So we would think that sodium was going to be So, or sulfur is just S. But I think Greek word for sodium is natrium, and so the Na refers to that. Gold is another one. Gold is Au. Silver is Ag. You don't have to memorize these. You'll come to know those 6 most common ones because we'll be using them a lot, but you don't have to memorize anything on the periodic table. But these different names are a little bit harder to get to know because they're a little not what you would expect. I remember a few years ago, Chipotle had some special burrito that it was making, and because it was special, I don't remember what was special about it. It was wrapped in gold foil instead of aluminum covered foil. And I remember that they had a billboard, I think on the 202, and they had a picture of the burrito wrapped in gold foil, and they had, the only words on it were AUSOM, meaning awesome. And so they were using the AU of the gold kind of as a joke. I always wondered how many people understood that that's what they were doing, or didn't just think that they spelled awesome wrong on the billboard. So those are the symbols that are used to represent an atom. Each atom has a specific mass because it has a specific number of protons and neutrons. And again, what determines what element a atom is the number of protons. So number of protons is also called atomic number. And the periodic table is arranged by atomic number. So they go from the lightest, so hydrogen is the uppermost. It only has an atomic number of 1 because it has just 1 proton, and then it just keeps adding protons as it goes through the periodic table. And if you remember, the things that give mass are protons and neutrons. So the mass of an atom is the sum of the protons and neutrons. So if there was like 3 protons and 4 neutrons, that would equal atomic mass of 7. The number of electrons is always the same as the number of protons because the charge is 0. So if you have 3, plus protons, you need 3 negatively charged electrons to balance out for 0. This is just a little thing to practice. If you use your periodic table, hydrogen has a symbol of H, atomic number of 1, because it has 1 proton. Hydrogen is the only element that actually does not have a neutron. So remember, to get mass, you add protons plus neutrons. So it's 1 plus 0, so it's 1. And electrons are always the same as protons, so it's 1. This is sodium. So its symbol is Na. It has 11 protons, so its atomic number is the same as the number of protons. Its mass is 11, so that means it has how many neutrons? Because you add protons and neutrons to get mass. So if 23 equals protons plus neutrons, if it has 11 protons, it would be 23 minus 11 equals the number of neutrons, so it would be 12. And then electrons are always the same as the protons, so that's going to be 11. So you can practice doing some of those, and you can check if you've got it right on the periodic table. So this periodic table, so for example, hydrogen has 1 proton, helium 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., all the way down to this guy here, which has 114. So again, it's the number of protons that determines what element a substance is, an atom is. So all carbon atoms have 6 protons. That's its atomic number. If you, again, would change that, it would no longer be carbon. If you took away a proton and it had just 5, it would not be carbon. If you added 1, it would not be carbon. And this is those 6 most common ones, just to show you kind of their structure. You'll see this shorthand sometime. This is this letter symbol. This here is the number of protons, so it's the atomic number, and then this number up here is the mass. So if you look here, hydrogen has 1 proton, mass of 1. Carbon has 6 protons, 12 mass. Phosphorus has 15 protons, so 15 electrons, and these are the 6 most common. Sometimes, I don't know why this is, some elements exist naturally in some different forms that are called isotopes. Now, an isotope has to have the same number of protons because remember we said that determines what element it is. So say, for example, carbon. To be an atom of carbon, you have to have 6 protons. But naturally occurring on the planet are 2 or 3 different forms of carbon. And what is different in them is the number of neutrons. So they all have 6 protons, but this is carbon 12. So it's got 6 neutrons. I'm going to go to the next slide because I think I have a better picture there. So here's carbon 12. It has 6 protons and 6 neutrons, and that gives it a mass of 12. Almost all of the carbon on Earth is carbon 12. So you have a lot of carbon in you because all your carbohydrates and fats and proteins and stuff making up your body are mostly carbon. So most of the carbon in your body is 98.9% of it is carbon 12. However, naturally existing, there's a little bit of carbon 13, and carbon 13, it has to have 6 protons or it wouldn't be carbon, but it's got 7 neutrons. And so that's why it's carbon 13. And then the rarest one, which is less than 0.1% of the carbon on the planet, is carbon 14. It's got 6 protons and 8 neutrons, and this one is radioactive. So some isotopes are unstable and they give off radiation as the due to the instability of the nucleus. And so whenever you see anything that's radioactive, it's because it's an isotope of an element that is unstable and it gives off radioactivity. So a little bit of the carbon in your body is actually radioactive. It's carbon 14. And some radioactive elements are more dangerous than others. There's different types of radiation. We're not going to really get into that. Some radioactive elements are used in different techniques for medical diagnosis. Carbon 14 is actually used because it decays at a certain constant rate. So for example, if while you're alive, you have all these molecules with carbon in them and 0.1% of it is carbon 14. Once you die, you're not making any more carbon, so that kind of begins to, it doesn't change. And so if they have found, but the carbon starts to decay, and so they have like found bodies that have been frozen for hundreds of years, and they can tell how long they have been decaying because of the amount of carbon 14 that's still there. And you may have, some of you work in a hospital, may have seen other radioisotopes used in medicine. If you have in the hospital, you might see the Department of Nuclear Medicine. That's the department that deals with radioactive elements. I think they say nuclear medicine because it's more appealing. Radiation is also sometimes used for treatment for cancer, and that's because radiation is poisonous to cells, and because cancer cells are growing more rapidly than other cells, they are more susceptible to the effects of radiation. Other rapidly growing cells are like hair cells and intestinal cells, so that if you get radiation for treatment of cancer, that's one of the reasons that you also can lose hair and have problems digesting food, is because it's also having an effect on some of the other cells in your body. They also can be used for imaging because it's easy to kind of detect the radioactivity. One method is to use radioactive iodine for diagnosing thyroid disorders. And radioactive iodine disintegrates pretty quickly, so it's not like you're exposed to the radiation for a long period of time. And you can kind of get an idea. This would be a normal thyroid gland, and so they would have administered radioactive iodine and look at its uptake. And this one is an enlarged thyroid gland. So it can be used for various diagnostic procedures. Again, I already showed you this. These are the 6 most common atoms and their models. What we're going to talk about in the next PowerPoint is chemical bonds. So atoms can join together and form molecules, like for example, water. Water is H2O, which means there's 2 atoms of hydrogen and 1 atom of oxygen joined together to form 1 molecule of water. So in the next PowerPoint or lecture, we're going to talk about how atoms can come together to form molecules and the types of ways that they can do that. And those are called chemical bonds. So that's what we're going to talk about next lecture. I was going to say next class. I have to kind of get myself into the groove of that we're not in class. So here's another one, sodium chloride, which is 1 atom of sodium and 1 atom of chloride bound together by a chemical bond. So that's what we'll talk about next. So again, there'll be a quiz. I think it's called like Chem Quiz 1 that goes with this information for you to take after you watch this one. See you soon.